So remember that last time we were talking about quantum error-correcting codes, and I'm going to continue to do that today. And today I want to talk a bit more about kind of the underlying mathematics of quantum codes, at least the most common kinds of quantum error-correcting codes, and go into more depth about their structure. So today we're going to be doing a lot of stuff with the polys. So I want to introduce a little bit of notation and some comments there. Sorry, say everything I wanted to. So of course, the polys, we had I, X, Y, Z. And they form the basis for the space of 2 by 2 matrices. So they're already useful when talking about quantum error-correcting codes because we knew that we only needed to correct the polys in order to correct arbitrary single qubit errors. And so let me define the poly group, which is composed of tensor products of I, X, Y, Z on, this is Pn, so it's on n qubits. And a group should be closed under multiplication. And so when you multiply x, z, you almost get y, but there's a factor of I in there. So we need a phase in order to make it a group. So we have overall phase plus or minus 1 plus or minus I. OK? And this poly group has a lot of nice properties, and we're going to be using some of those properties today when we talk about error-correcting codes. So first of all, well, it is in fact a group. It's closed under, which means it's closed under multiplication. The other thing about a group is it's closed under inverse. But in this case, that's a pretty simple thing because I, X, Y, and Z are all self-inverse. Of course, in the poly group, we also have phase of I, which is not self-inverse. I plus I times minus I is equal to 1. But that in particular, we find that any element of the poly group squares either to the identity or to minus the identity. And so another property of the poly group, which is a really important one, is that it's not an abelian group. It doesn't commute, but it's kind of almost abelian in the sense that any two polys either commute or anti-commute. And certainly for the single qubit polys, well, everything commutes with itself and everything commutes with identity. But X, Y, and Z all anti-commute with each other. So you might think that this is not a very interesting observation. And you could just say, well, the non-trivial things all anti-commute with each other. But that's only true for 1 qubit. For 2 qubits, you can get much more interesting things that happen. So for instance, X tensor X commutes with Z tensor Z. Right? Because you move XX past ZZ, you get 2 factors of minus 1. Okay? So you get lots of non-trivial cases where they commute as well as cases where they anti-commute. Okay? So there's lots more properties of the poly group, but these are kind of some of the main ones that I'll be using. And I just wanted to write them up because we'll be using them pretty shortly. Maybe I'll switch forward. So last time I introduced the 9-qubit code, which I guess I'll write down again to review it. So the logical 0 there was 0, 0, 0 plus 1, 1, 1, tensored 3 times. And the logical 1 was 0, 0, 0 minus 1, 1, 1. And so now I kind of sloughed over a little bit exactly what you have to measure in order to find the error synchrome for this 9-qubit code. It's very much analogous to what you do for the 3-qubit code, but it's not identical. So let me talk about that in a little bit more detail, although without writing down the full circuits to do it. So, and in particular, I want to introduce a slightly different point of view on what we were doing before. So before, I said for the 3-qubit code, which, remember, the repetition code is kind of implicit here. So within each set of 3, in this case, we want to look to see which qubits are different, which qubit is different from the other 2, right? And we broke that down into 2 steps. Are the first 2 qubits the same or different? Are the second and third qubits the same or different? But that's a kind of a classical language. Are these 2 bits the same? Do they have even parity? But what's a quantum language for the same thing? Well, we could say, is this state a +1 or a -1 eigenstate of some operator? And in particular, if you look at Z tensor Z, well, if both qubits are the same, 0, 0, or 1, 1, it'll be a +1 eigenstate of ZZ. Whereas if they're different, it'll be a -1 eigenstate of ZZ. Right? So same different is the same So what I want to start out by doing then is write down, within each set of 3, we're going to measure then the eigenvalues of Z tensor Z on, say, the first 2 qubits and the second and third qubits. And so I want to write down the list of things that we're measuring here. So I'm suppressing a whole bunch of things here. So each row is going to be an operator, which we're measuring the eigenvalue of. And I'm suppressing the tensor product. So the column is supposed to just tell you which qubit it's in. And because there's a lot of i's, really, this first one is Z tensor 7 i's. I'm not going to write out the i's either. OK? So I'm only going to write the non-trivial Paulis in each tensor product. So this is the first one, ZZ on the first 2 qubits, and then ZZ on the second and third qubits. Then we have to do the same thing for the next block of 3. So we get ZZ here on qubits 4, 5, 5, 6, and 7, 8, 8, 9. OK? So that covers what we measured to figure out the bit flip errors. Now what about the phase flip errors? Remember, the phase flip errors, we're supposed to see whether these signs are the same or different between different sets of 3. So analogously, we want to compare the first 2 blocks of 3 and say, do those 2 blocks of 3 have the same sign or different signs? And from the analysis of the 3-qubit phase code, remember the Hadamard transform switched the role of x and z. And so while we were measuring, and so for that 3-qubit code, instead of measuring ZZ, we should measure XX eigenvalue. For this 9-qubit code, that's not quite going to work, right? Because if we take, say, X on the first qubit and X on the 4th qubit, these states are not eigenstates of that operator, right? Because X on the first qubit will give us 1, 0, 0 plus 0, 1, 1, or minus 0, 1, 1. And that's not one of the valid code words. So what we want to do is flip all 3 bits in the set of 3. Right? If we take x tensor x on the first 3, that'll take this to itself, 0, 0, 0 plus 1, 1, 1 to 1, 1, 1 plus 0, 0, 0. 0, 0, 0 minus 1, 1, 1 becomes minus 0, 0, 0, minus 1, 1, 1, right? So this 3-qubit state is a +1 eigenstate of XXX, and this one is a -1 eigenstate of XXX. Now, that's not exactly what we want. We want both code words, or all code words, any superposition of those, to be a +1 eigenstate. And so what we need is not, but this is just telling us what the sign, the 3 x's are just telling us what the sign is on the first block of 3. And we want to compare the first block of 3 with the second block of 3. So what we want is the tensor product of 6 x's. So putting that into our list here, we get x, 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 x. OK? And indeed, the valid code words are +1 eigenstates of this. But if you have a state where one of the signs has been flipped, and so say the first 2 signs, in this case, the first 2 signs are different, then it will be a -1 eigenstate of this. OK? And then we have to compare the second and third signs. So we do 6 x's on qubits 4 through 9. OK? And this gives us enough information to figure out the error synchron and figure out what the error is, and then correct it. OK? So are there any questions on this?
So you don't need any ancillas or anything?
Well, I haven't told you exactly how to measure these eigenvalues. In the case, I mean, the most natural way to do it does use ancillas, right? And in particular, there's a reasonably straightforward way that uses 1 ancilla qubit for each of these operators. Right? That's what we were doing with the 3-qubit code. We said, well, we'll do some C0s from the first 2 qubits, and that will tell us whether they're the same or different. And that's a way of measuring that eigenvalue of ZZ. And you can do something similar for all of these. Now, in the communications context, where we don't have to worry about gate errors, then actually it's possible to kind of combine decoding with the error synchron measurement, and then you don't need any ancillas at all. But that's a little more complicated. Any other questions? OK. So one thing that you might wonder is, well, did we have to measure these particular things? So for instance, we want to see if the first 3 qubits are the same, which one is different, right? And I said, oh, let's measure the first 2 and the second 2. But what about the first and the third, right? If all 3 are the same, the first and the third have to be the same also, right? And so why didn't I put that on this list? And the answer is, well, you certainly could have measured that. The valid states are +1 eigenstates of Z, IZ. If the first and the third qubits are different, then it'll be a -1 eigenstate of Z, IZ. But the reason I didn't write it is because it's a product of this and this, right? Z, IZ is this times this. And if the state is a +1 eigenstate of this and a +1 eigenstate of this, then it's certainly a +1 eigenstate of Z, IZ as well. So that's kind of dependent. It's not a new thing to measure. And in general, if it's an eigenstate of both this and this, whether +1 or -1, the eigenvalue of Z, IZ is determined by these 2 eigenvalues. OK, so while this choice of things is not unique, it is kind of gives us all the information that we could get by measuring all the other possible polys that would tell us something about the error. OK, so in particular, let's define the stabilizer of any code, but in particular the 9-qubit code. So the code is going to be some subspace of the Hilbert space, right? And what I've been doing so far is giving you basis vectors of that subspace and then saying, well, everything else is superposition. So what's that saying in this case is that it's a 2-dimensional subspace. So T is a subspace of the Hilbert space. So the stabilizer is then the set of Paulis such that m psi is equal to psi for all psi in T. Okay? So it's a set of Paulis that have +1 eigenvalue for every code word. Right? So in the example of the 9-qubit code, XXX on the first 3 qubits is not in the stabilizer because it's only 0 bar. The logical 0 has a +1 eigenvalue, but the logical 1 doesn't. But this tensor product of 6 x's is. Okay? And for the 9-qubit code, these 8 operators here generate the stabilizer. The stabilizer consists of all the products of these things. Okay? So the stabilizer is always an abelian group. So why is that? Well, intuitively, this should not be surprising, right? Because if you want to have a simultaneous eigenvector of some different operators, you want them to commute in general. Okay? But it turns out that's not completely true. There's special cases where that's not the case. They have to commute on the subspace. But in the case of Paulis, it is true. And let's just prove that formally. It's not too hard. In particular, if m and n are in the stabilizer, then mn applied to psi, well, that's equal to n psi is equal to psi. So it's equal to m psi, and m psi is equal to psi as well. This is true for all psi in the code. So this is, first of all, this is a proof that the stabilizer is closed under multiplication, which I already kind of argued before, but there it is. And similarly, nm psi, by the same argument, is equal to psi. And so that implies that the commutator applied to psi is equal to 0. You just subtract them off. Okay? And so here you can see that in the general case, for general operators, it actually doesn't require that m and n commute. It just has to be that psi is in the null space of the commutator. But m and n are in the Pauli group, and that means that either they commute or anti-commute. And if m and n anti-commute, then that means the product of them is proportional to another Pauli. Okay? And sorry, in particular, the commutator of them then is proportional to another Pauli, which doesn't have any 0 eigenvalues. Okay? So that implies that in this case, mn actually is equal to 0. Okay? So it's an abelian group. Okay. And another observation, this one almost trivial. So minus the identity is never in the stabilizer. Okay, and I won't even write down the proof for that because it's so easy. The stabilizer just consists of things that have +1 eigenvalues. So minus I has no +1 eigenvalues. Okay? And so it turns out that these properties are always enough to define a stabilizer. So if you have these two properties, then the group will be a stabilizer of some code space, which could be a one-dimensional code space. So it could just be a single state, but it could be a bigger code space as well. Yeah, and so that's a useful thing to do because that means that we can then, rather than writing the code words, we can write the code words and define a stabilizer. That's what I've done so far. But the thing is, the stabilizer is actually a much more efficient way of describing the code space in general than writing the code words. I mean, for these particular code words, they weren't too complicated. But in general, if you have an n-qubit space, right, a single state can be a 2 to the n dimensional. I mean, it's somewhere in this 2 to the n dimensional Hilbert space. So you might need 2 to the n, maybe 2 to the n minus 1 due to normalization, complex numbers to describe the state, right? Just one state. Whereas the stabilizer, well, it required many fewer things. I guess I haven't proved this yet, but this description here, there's going to be at most n generators of the stabilizer. I don't have to list everything in the stabilizer. I just have to list the generators to define the group. And there's at most n of them. And each of them is n qubits long, so that's about an O of n squared size description of this subspace. Whereas describing the states in terms of the amplitudes, that's O of 2 to the n. OK? So that's potentially the stabilizer is potentially a much more efficient description. So for that reason, among others, it's convenient, when possible, to, instead of writing down the code words and describing the stabilizer, we want to write down the stabilizer and talk about the code from that perspective. So how do we do that? So suppose we're given some S, which is a subgroup of the polygroup. And minus the identity is not in S. And then we can define the code space for this stabilizer to be the set of vectors such that m psi is equal to psi for all m in the stabilizer. OK? So it's kind of, we've just reversed the quantifiers from the definition of what a stabilizer is from a code. Yeah?
Just a question with your earlier argument about scaling. Can you repeat why there should be at most n generators?
Yeah. So yeah, let's see. So here's a kind of argument that there's at most 2 n generators, and actually it's less than that. So the polygroup, how many elements does it have? It has 4 to the n elements. OK? And so what are the generators of the polygroup? Well, one set of possible generators is x and z on each of the n qubits. And so that's 2 n generators. And because this polygroup has a very simple structure where everything either commutes or anti-commutes, then you're never going to need more generators than that for any subgroup of the polygroup. Because it's always an abelian group, you can't even do that, right? Because x and z are kind of incompatible. So you could have z on the first qubit and z on the second qubit, but that's only going to get you're kind of getting 1 generator for each qubit is n. So that's not a full argument, of course. There's a pretty straightforward linear algebra argument that shows it completely, but I don't quite want to get into the details of that.
Thanks.
Yeah.
So the T of S, can it be defined as the invariant subspace under just the generators, or do we have?
Yeah. So right. So suppose you have a state that satisfies this for all the generators. Well, then it's also going to satisfy it for any product of the generators, right? Just it's that same argument there, that if m psi is equal to psi and n psi is equal to psi, then mn psi is equal to psi. So it's enough, yeah, to check it just for the generator. Okay? Anyway, so the point is this definition, we're just taking the states that are those joint +1 eigenstates under all the operators in the stabilizer. Okay, and that's going to define our code space. So in this case, we say that T of S is a stabilizer code. And frequently, I'll just talk about S, the stabilizer, as being the code itself. Okay. Now, not all quantum error correcting codes are stabilizer codes. You know, for n qubits, there's only a finite number of possible stabilizers. There's only a finite number of stabilizer codes. But you can take, you know, an arbitrary subspace you can think of as a quantum error correcting code. It might be a bad quantum error correcting code. Although when n is large, it turns out typical subspace is pretty good quantum error correcting code. But there are many codes that are not stabilizer codes. However, stabilizer codes are the ones that most often you will see because they're the easiest to work with and have the most structure. OK, so the first question you might ask, well, suppose we write down this stabilizer. How big is the code, right? When we were writing it down the other way, well, we were writing down the basis vectors, and so we immediately knew how many logical qubits there were. But for stabilizer, it's maybe a bit less obvious. But it's still derived very easily. So when the stabilizer has R generators, first of all, the stabilizer has 2 to the R elements. So that one's fairly obvious because it's an abelian group, and everything has to square to +1 because -1 is not in the stabilizer. So you just, you know, each element of the stabilizer is a product of distinct generators. And it's just a question of which generators you have in the product. And so there's 2 to the R possible subsets. And therefore 2 to the R elements. So the next thing is more interesting, which is the number of encoded qubits. So we're going to let k equal n minus r. And then the code has k logical qubits. So the dimension of the encoded subspace is 2 to the k. So the code encodes k qubits. OK, so I'm not going to prove this. And the way you prove it is this linear algebra argument that I was giving. You'll see that this theorem also implies that the maximum number of generators is n. Because if r were greater than n, k would be negative, which is nonsensical, right? Because then dimension would be 2 to like a half or something. Not a meaningful thing. But I can give you a good intuition as to why this theorem is true, which is suppose we just have one generator, right? So it's a Pauli. It's a tensor product of Paulis. It splits the space into a +1 eigenspace and a -1 eigenspace. And they're both half the dimension of the whole Hilbert space, right? So that's the case of r equals 1. We have a 2 to the n minus 1 dimensional +1 eigenspace for that operator. Then when we pick a second generator, it's splitting it in half again, right? And so now we have a 2 to the n minus 2 dimensional subspace. And the third one splits it in half again, 2 to the n minus 3, and so on. OK? Every time we pick a generator, we're dividing in half, and so that gives us this formula. Now, the argument I just gave you is not a proof, because you have to show that every time you're picking one, certainly it's dividing the whole Hilbert space into half, but is it dividing these subspaces into half again? And the answer is yes, provided you're picking them independently. But that's the part that requires some proof. OK? OK, so this is one of the properties that you want of a code. The next property, of course, is correcting errors, right? How good is this at correcting errors? And we already have a hint that the stabilizers are going to be useful for that, because that's how we wrote down the stabilizer for the 9-qubit code, right? By saying, what eigenvalues do we have to measure to determine the error synchron? And that's going to be the general case, that for the general stabilizer code, the error synchron will be the eigenvalues of the generators of the stabilizer. But we can go a bit further than that. And we can make a concrete connection between the elements of the stabilizer and the things that we can identify, the errors that we can identify. So in particular, you remember the ZZ operator was useful for identifying bit flip errors. Right? It says if we had a bit flip error on one of the first 2 qubits. And similar, if we had XX, say for the 3-qubit phase code, that would be good for identifying Z errors. OK? So you see that the polys are good for identifying errors that are other polys. And the key point here is that those things anti-commute. So in particular, so let M be in the stabilizer. And we'll take 2 cases. So suppose we have an error, E. And E is also going to be in the poly group. And in the first case, we'll let which one should I do first? We'll let them anti-commute. So E and M will anti-commute. Well, then let's see what E does. So the state psi was in the code. And so M psi is equal to psi. Psi is a +1 eigenvalue of M. Let's look at the eigenvalue of E psi after we have the error E. Well, E and M anti-commute. So we can switch the order, but we get a minus sign. And M psi is equal to psi, so this is minus E psi. OK? So E psi is now a -1 eigenvector of M. So conversely, suppose E and M commute. Well, we can do the same argument, but we don't get the minus sign. We instead find ME psi is equal to EM psi, which is equal to E psi. And E psi is still a +1 eigenvector. So the upshot is that measuring the eigenvalue of M tells us, if we had a poly error that occurred on the state, it tells us whether that poly error commutes or anti-commutes with M. OK? And so that's the basic idea of how we're going to do error correction. We're going to pick, well, we're going to have the generators of the stabilizer. We're going to measure their eigenvalues. And then each one will give us some information about what the error was. Right? And hopefully, we've designed the code in such a way we can put that information together to figure out what the error is. And in particular, it's clear that OK, so let me be a little more precise about that. So we say the error synchron of an error E in the poly group is a vector which is 0 or 1 on bit I if E commutes or anti-commutes with the generator mi of the stabilizer. Okay. Now, obviously, this definition of error synchrome depends on the specific choice of generators and even the order that I put it in. But given that order, the error synchrome then is a property of the error. Okay. So the other thing I want to define is the set n of s. So set of n of s is the set of n in the Pauli group, such that m and n commute for all m in the stabilizer. Okay, so this is the set of things that commute with everything in the stabilizer, and therefore the set of things that have 0 error synchrome. Since the stabilizer is abelian, the stabilizer is always in n of s. But in general, there's other things in n of s as well. And those things are going to be undetectable errors, right? Because those are things that commute with all the things in the stabilizer and therefore have 0 error synchrome. And therefore, we have no way of distinguishing them from the identity based on the error synchrome. OK? But actually, I would be a little more concrete about that. So the set of errors, Pauli errors, that cannot be detected is n of s minus s, okay? Which I actually did say before, but I want to make it more emphasis. So certainly anything that's outside of n of s can be detected, right? Because it has a non-zero error synchrome. But anything that's in s, why would I say that that's a detectable error? Well, if it's in S, then what does it do to a code word? Well, E is in the stabilizer. Sorry, what did I write here? If E is in the stabilizer, then E psi is equal to psi. Right? And so E psi is not really an error. It left the state alone. It didn't change the state. It's acting the same way as the identity, in fact. Okay? So anything that's in S, while it certainly commutes with everything in a stabilizer, is not really an error in a meaningful sense. And therefore, it's only the things that in E of S minus S, well, anything in N of S minus S, that means that there's some psi for which this is not true. So here's a state in the code that gets changed by this operator, but nevertheless, the operator cannot be detected from the error synchrome. So that's a real error that's undetectable. Okay? And so those are the things we need to avoid. Okay? Any questions on this? Okay, so that's detecting errors, but we can go from there to correcting errors, and I've already kind of given you a hint how, right? So this is just saying, well, is the error synchrome 0 or non-zero? But what we really like to say is we'd like to have, for each error, we'd like to have an error synchrome that tells us what it is. And the different error synchromes certainly give us some information about the errors. And so under what circumstances can we actually correct the set of errors? So the stabilizer S, or the code associated with it, can correct a set of errors if you take the product E dagger F, and that's outside n of s minus s for all pairs in the set. Okay, and I probably should make the constraint that this is a subset of the polygroup. Okay, so why is that? Well, so if E and F have different error synchroms, then I can distinguish them, right? So when do E and F have different error synchroms? That's saying that there's some m in the stabilizer that commutes with one of them and anti-commutes with the other. Okay? I mean, it could be either one. It could commute with E and anti-commute with F, or it could commute with F and anti-commute with E. But either way, if I take the product E dagger F, then that will anti-commute with M. Now, taking the dagger doesn't really matter because we're dealing with polys. It's at most a sign of +1 versus -1. But when you generalize this to other contexts, higher dimensional qubits, then it starts to matter. OK, so we have E dagger F anti-commutes with M. And that's saying then that E dagger F is outside n of s. OK? So if for all pairs E dagger F was outside n of s, then we'd be done. Because then we could say, oh, the error synchroms for all the errors are distinct. Right? And so just by looking at the error synchrom, we would know what error occurred, and then we could correct it. Because they're all polys, they're all unitaries, so we can just invert them once we know what it is. OK? But what about the case when E dagger F is in S? So if E dagger F is in S, then, well, the same thing holds. E dagger F psi is equal to psi. And then if we multiply by E on both sides, we find that F psi is equal to E psi. OK? So if E dagger F is in S, then that means that E and F act the same way on code words. OK? We can't distinguish them by looking at the error synchrom, but we don't need to because they do the same thing. So what these two things are saying is that when E dagger F is always outside n of s minus s, we'll be left with sets of errors that are indistinguishable on code words. And each of those sets has a different error synchrom. And so by measuring the error synchrom, we know which set of indistinguishable code words we have. And we can just pick one example from that set and correct it, because they all act the same way. It doesn't matter which one we pick. OK? And so that's why you can correct this set of errors. OK? Does that make sense? OK, so this theorem then gives us a nice criterion that we can look at. Given a stabilizer, we can determine if it corrects a set of errors or not. So for instance, if the set of errors is all poly errors on a single qubit, you can figure that out just looking at the stabilizer. You don't have to go through that thing where you convert to the to the subspace and then work from there. This is purely in the operator side. OK? And so then one more definition. There's one more blackboard up there, but whatever. So we say the distance of a stabilizer code is the minimum weight of an element of n of s minus s. So the weight is the number of qubits it acts on non-trivially. So if it's a tensor product of I on some and xyz on the others, it's only where the xyz's are. You count how many there are. That's the weight. And this is saying this is you take the smallest weight thing in n of s minus s. So that's the smallest undetectable error. And the weight of that is the distance. OK? You can think of it as the fewest number of qubits you have to act on to get from one code word to a different code word. And we say quantum error correcting code is degenerate if S contains a non-trivial element with weight less than the distance. Otherwise, it's a non-degenerate code. Okay? And so this is just saying that if we get this case where you have two errors that are doing the same thing to code words, it's degenerate. And then we say some notation. So we have a code with n physical qubits. I guess this should be a stabilizer code. K logical qubits. And distance d. We write this with double brackets like this, and then we put nkd. So these are kind of the main properties of the code that you're usually interested in. And the reason for that is if you look at this theorem, you'll see that distance 2t plus 1 code corrects t errors. Right? Because suppose our set of errors, script E, is a set of all errors of weight up to t. Well, then if you take the product of two of them, the product of two of them has weight up to 2t. But if the distance is 2t plus 1, then something of weight 2t cannot be in n of s minus s. And therefore, that theorem up there holds. And we can correct that set of errors. OK? So in particular, if you want a code that corrects all single qubit errors, then you need a distance 3 code. OK? Yeah?
So can you explain the significance of the degeneracy idea?
Sort of. Basically, so the reason why I emphasize this as a definition is because classical codes don't have degeneracy. This is a property just of quantum codes. And it therefore complicates the theory of quantum codes a lot. I don't really want to go into how, because I'm almost out of time and I have a couple other things I want to do. But I will point out that we've already seen a degenerate code. This 9-qubit code is a degenerate code. right? And you can see that two ways. So one of them is just to note that it's a code that corrects one error. So it could have distance 3. But look, in the stabilizer, there's some weight 2 things, right? And the other way, which is obviously completely equivalent, is to say, well, what if we have a phase error on the first qubit versus a phase error on the second qubit? Those give us the same state, right? 0, 0, 0 plus 1, 1, 1 in either case becomes 0, 0, 0 minus 1, 1, 1. Okay? So the errors are not distinguishable. OK, so OK, so let's look at some more examples of stabilizer codes. So I said yesterday that the 9-qubit code is not the smallest code. So what is the smallest code to correct one error? That's the 5-qubit code. OK? And so that code is a 513 code. So 5 physical qubits, 1 logical qubit, distance 3. So it corrects one error. And here's its stabilizer. So this time I'm going to write the I, but I still don't have the tensor products. Each row, remember, is a generator of the stabilizer. So one nice thing about this code is that it's cyclically invariant. Each one here is a cyclic permutation of the other ones. You might say, well, what about the 5th cyclic permutation? It's the product of these. So I didn't need to write it down separately. And OK, so we have here 4 generators, 5 qubits. So that means 1 logical qubit, as I said here. Distance 3, well, you have to do a bit more work to see that. But and then there's 2 ways to do it. One, you could take any single qubit error. This is a non-degenerate code. And if you write any single qubit error, it has, and figure out its error syndrome, it has a different error syndrome. Or you could take an arbitrary 2-qubit thing and see that it anti-commutes with at least one of these generators. OK, I'll leave that to you if you want to do it yourself. So another nice thing about this code is that there's how many errors are there? Well, there's 5 qubits, and each of them could be x, y, or z. And then there's the identity. So there's 16 possible errors. And I said it's non-degenerate. Each one of them has a distinct error syndrome. How many error syndromes are there? Well, each of them is 4 bits long. So there's 2 to the 4 error syndromes. So this is what's known as a perfect code, where all of the error syndromes are used for the errors that we're correcting. That's not generally the case. Most codes have kind of some extra error syndromes. But it gives you a hint that this is an optimal code. That's not actually a proof, because there could potentially be a degenerate code that's smaller. There isn't. And there's a very nice proof of that using the no-cloning theorem, but I don't have time to do it. So this is, in fact, the smallest quantum error correcting code that corrects one error. OK? So another nice code is the 7-qubit code. Maybe I'll skip the I's on this one. So the 7-qubit code, 6 generators, 7 qubits, therefore 1 logical qubit. So that gives you the 7 and the 1. The 3, again, is a little more complicated. But in this case, it's derived in a nice systematic way. Actually, you can do that for the 5-qubit code too, but I didn't. So you'll notice that here we have 3 generators that are all x's and 3 generators that are all z's. Okay? And so these z's, for instance, are saying the state has even parity for these first 4 qubits, or for these 4 qubits, or for these 4 qubits. So that's kind of a classical error-correcting code property. And indeed, these 3 generators here define a classical code. And these 3 generators here define a classical code as well. That's just in the Hadamard basis. So this is a phase error-correcting code. This is a bit flip error-correcting code. And so what we can do to derive this code is we can look in the classical coding theory literature and say, well, what's a good code to use? We'll take 2 codes, in fact. One of them will turn into this phase code, and one of them will turn into the bit flip code, correcting code. In this particular case, they're the same code. They're both the 7-bit Hamming code. But once we do that, we hopefully can derive a quantum error-correcting code. The thing is that we can't just let these codes be arbitrary codes, right? Because remember, the stabilizer has to mean a billion group. And certainly the x's all commute with each other, the z's all commute with each other. But it's not a given that the x's and the z's commute. In this case, you can see that they do. But in order to make that true, we want to make sure that something called the dual of this code C2 is a subset of C1. Okay? And when that's true, you can pick 2 codes that have that property, and then you'll always get a quantum code. And the distance of the quantum code is at least as great as the smaller of the distances here, because this code will correct as many bit flip errors as C1, sorry, as many phase errors as C1, and as many bit flip errors as C2. Okay? It could actually correct more because of the potential of degeneracy, but it will certainly do at least as well as the 2 classical codes, the worst of the 2 classical codes that it's made from. Okay? So you might ask, well, why do you care about the 7-qubit code if we have the 5-qubit code, which is smaller? And there's 2 reasons for that. One is because it's an example of this general construction, which is a pretty useful one. And the second is because this particular code is very good for fault tolerance. So in the last 30 seconds, and probably a little bit more, I'm afraid, let me say a little bit about fault tolerance. So when we want to build a quantum computer, remember, we can no longer assume that the gates that we're using to make the code words are perfect, right? There will be errors in those gates. And so there's various things we have to be careful about when we want to deal with error-correcting codes. We want to do error correction. We want to create the states. And we want to do gates on the logical states. And one of the things we have to be careful about, one of the main things, is error propagation. Okay? So for instance, if we do a C0 gate between 2 qubits, but there's a bit flip error up here, the gate itself is going to be perfect in this particular example, but we already had a bit flip error. Well, that means that this qubit is 1 when it's supposed to be 0, and it's 0 when it's supposed to be 1. And so this qubit down here is going to get flipped when it's not supposed to, and it's not going to get flipped when it is supposed to. So if we had an x up here, now we have x's in both qubits. And similarly, if you have a z error down here, you can work out that it propagates backwards, and we'll get z errors on both qubits. So that's what we have to worry about. Well, that's one of the main things we have to worry about. We have to worry about error propagation. That existing errors, even if the gates have no errors in them, an error that occurred in an earlier gate can propagate through our 2-qubit gates to make more errors, right? And that's a problem because suppose we have, say, the 7-qubit code, and we started with 1 error. Well, that's OK. It can correct 1 error. But if it propagates and now there's 2 errors, now we won't be able to correct that, because the code doesn't, in general, correct 2 errors. So what we have to do is we have to be careful about how we design our quantum circuits. So in the case, yeah. So one thing we can do is suppose we take 2 blocks of the code. So let's imagine that this is, I drew 7 lines, and this is a 7-qubit code, and this is another block of the 7-qubit code. So it's 14 lines altogether. So we have 2 logical qubits encoded separately in the 7-qubit code. And suppose we do a gate that looks like this, where we do a C0 from the first qubit of the first block to the first qubit of the second block, and from the second qubit to the second qubit, and the third qubit to the third qubit. So this is called a transversal gate, a gate that has this structure. And now, while the errors can propagate, they won't propagate within the block. If we have one error up here, it propagates down here. And now we have one error in this block of the 7-qubit code and one error in this block of the 7-qubit code. And each of those blocks can correct one error. So we're still OK. OK? And that's why the 7-qubit code is very useful, because it has a wide variety of gates that you can perform using this transversal construction. Unfortunately, you can't do a universal set of gates that way. And so you need some additional tricks, and this is where fault tolerance starts to get very complicated. Error correction is also pretty complicated. So I'm not going to go into the details of that. But the bottom line is that there exist protocols that let you do a universal set of gates and perform arbitrary circuits encoded in a quantum error correcting code. Okay? And when you do it this way, the logical error rate of the encoded circuit is going to be lower than the logical error rate would have been if you had not encoded it. Okay? So the fault tolerance is actually helping you reduce the error rate. And then from there, you can go to the threshold theorem, which says there exists some threshold error rate, P sub t, such that if the error rate per gate or time step is less than pt, there exists a fault-tolerant protocol for arbitrarily long quantum computations. And that protocol can achieve an arbitrarily low logical error rate. Of course, you might ask, what's the cost of doing this? You need to do extra qubits. You need to do extra gates. But the overhead, meaning the ratio of, say, the number of actual qubits, physical qubits, to logical qubits, or the number of physical gates to logical gates, is some polynomial in the log of t over epsilon. So let's see. The error rate that we're trying to achieve is epsilon. And this thing is length big T. OK? So if we want to do a really, 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 really long computation with a really, really, really low error rate, we can do that, and the overhead is still only modest. Obviously, you still have to do all those many, many, many gates. You can't get out of that. But the extra cost of doing error correction is not crazy. OK. Now, in practice, the numbers are still pretty large, right? This is kind of a big O notation, so I've suppressed the constants, which sort of, for reasonable size means you have to blow up by, say, 1,000 qubits or more. So that's a pretty big cost in practice. This threshold error rate seems to be of order 1% for simple error models. And so, kind of if you get the physical error rates down to what we were talking about 2 weeks ago, of order 0.1%, that's probably good enough to build a big quantum computer. Now, if you can get it lower, that's better, because then you'll need less error correction. But But at least, theoretically speaking, we're in the right ballpark where the fault tolerance and the encoding in error-correcting codes can kick in once the experimentalists get this error rate down below this threshold value. And so that's why this is kind of the main theorem, the central theorem of fault tolerance. It tells us that the task of building a quantum computer is at least theoretically possible, right? You only have to get the error rates down to a reasonable point and then the software can kick in to make it possible to build a big quantum computer. OK? The proof of this, well, the details are a bit complicated, but the basic idea is quite simple. I said we have a fault-tolerant encoding that will reduce the error rates. And so the idea is, well, if you can encode it using this fault-tolerant protocol and reduce the error rates once, why not do that again? You take the encoded version and encode that using the same fault-tolerant protocol, or a different one if you prefer. And that will reduce the error rates further. And by doing that a few times, you can get this error rate down to as low as you like. And that's how you can get also arbitrarily long computations. OK? OK. So sorry I ran a bit over there. I guess we have a tutorial today where you'll get some more practice with stabilizer codes and their properties.